Oh, I haven't been talking this whole time. That's funny. All right. So let's check the minimum of the function that. Bro, I was talking and I realized I had my mic turned off. So let's just check. We did this minimum wrong. Uh, the minimum value should be 3/4. This is just wrong, right? This is just wrong. But why? That's an interesting question. So let's try to figure out why it's wrong. So the main reason that we're doing that it's giving out the incorrect answer is bro, I forgot to square the thing. So let's just try that. Okay, still returns 7, which is rather weird. Um, and instead, this should be able to do more ranges. So let's try that. Yep, 3/4 exactly. Wonderful. The problem is in Python you can't use comma like that. Just can't. I'm pretty sure there's a better way to do it. Maybe you could just pass in the iterations, but yeah, it's pretty decent. Gets us the exact value we want. Um, so yeah, we found the global minimum. So we should give a different function now. So let's do this function right here. So let's change func1 to the function over here. So x cubed minus x to the power of 4. So I know I kind of not really got into exactly how gradient descent works, but I guess I sort of thought it was kind of intuitive. But if you guys want, you guys can check out the book. Maybe I'll link it in the description if I get around to it. But you can just Google it up. Um, just find it on for free on the guy's website. He's from what I've heard, he's a pretty nice guy. Pretty cool that he runs Math Academy, I believe. It's pretty cool that he's helping upskill a lot of people. Kind of cool. Anyway, so let's just do. Okay, yeah, whatever. Let's just end it here for next part 1. Oh, we don't even need it, but okay, fine. There's an overflow error, right? Because our values are being picked too big in the derivative, so it's over here mainly. So obviously we can remove this piece of code. But yeah, 3x to the power of 3x squared minus 4x cubed. Um, hmm. Uh, like this being caused. Okay, yeah, so it's obvious why the problem is being caused. The numbers are getting too big here. Um, so what I think is, what let's just try, something we could try, is first of all, lowering the alpha learning rate. That seems like a pretty first decent step to debug. Let's try that. Now the overflow error still occurs, obviously. Don't know why I thought. You could Am I tripping? Why is the x getting so big? Um, okay, let's try with 10 iterations, or else it's just getting passed in immediately. Okay, that is a minimum of this function. Uh, kind of, okay. But now let's just 100 iterations, and it happens at 100. So somewhere between 50 and 100 iterations is, I mean, sorry, 10 and 100 iterations is what's happening. Okay, so it's happening here. So let's try 30, and then we can use that to sort of debug where it happens. Okay, so 30, between 30 and let's try 40, obviously 40, and let's try 45. Probably 40 will happen, which didn't happen. So I guess my intuitions need to be adjusted there. Seems like they're not very good. So it happened at 50. Yeah, 49 it happens. 48 it should probably happen. 47 it shouldn't happen. 47 should happen. Okay, 46. Maybe it's just 45. Okay, 46. Right? So let's print the current x guess. If um, that if you do it one more time, it immediately crashes the derivative. That's not too bad, actually. 1.16 shouldn't be causing an error. I guess, okay, one way we could do try except loops. So that's an ugly temporary solution. Let's just put a try loop, try, and except, there's a overflow error. It should immediately print the current value of except overflow error. So let's just print the current guess. Oh, I'm already printing it. Let's just tab this in one. Um, this is that's pretty solid. Um, why does this not? Okay, you know what? Just I don't understand where the overflow error is coming from. Okay, I'm somehow stuck. I can't get back to my whole computer might have went black. Ooh. Okay, we were making a slight mistake, but the error still cost. I thought the error was that we were making supposed to be less than, but even with that, the error still caused. Sorry, what line is this being caused on? Just for, I guess, for some reference, this is being caused on line 17. Oh, the problem is being here is being when you're calling the function of it. Right. Um, can you do a return statement here? Okay, let's just put a couple find errors. Try excepts are really useful. So let's just print x. Let's see what's passed in. None type, right? E to the power of 80. Wait, that's 10 to the power of 80. Where is that number coming from? So obviously the number is going to be in potential mins. Okay, so now we need to, so we can remove this overflow error, this except catch, right? So the error has to be somewhere in the potential mins, and so if it's in the potential mins, that means that it's in the current guess, right? So let's print the potential mins, I suppose. That's one way to do it. This is for I and first guesses. Okay, so we're setting current min here, so let's just print potential mins. So how many of these are there? Maybe 5. Yeah, remove the try block. Bad indenting, it won't like that, so it's just indent better. Okay, cool. Uh, whoa, whoa. Okay, these two are reasonable. They are within reason, but this last number is ginormous. Where's that coming from? Okay, so we try it over for I and first guess. So it's 0, 1, and 2. So when we do 2, it should be returning this number, unfortunately. Uh, which kind of does make sense. 2 grows very, very quickly when you exponentiate it. And the derivative of this is going to be positive. It's going to be kind of negative once you get high enough, actually. Yeah, it's going to become very, very negative. So that's kind of weird. It shouldn't be growing too much, considering the derivative is a 40 to the negative 80 is pretty big. Okay, I'm gonna try instead of 1/2. I'm gonna try 1/2 instead of. Oh yeah, we should be positive 9. Yeah, this makes sense. We were making so negative 1.66. Okay, so let's take this function now. Let's find what the actual thing should be. So let's just Google it. Apparently the minimums are, bro, just tell me what the minimum should be. Bro, what? Okay, x equals 0 is a local min. And that should be it. But the reason that this happens is because the function, as you get to really high numbers, um, suppose we could change this from 47 to 47,000. Yes, some fun overflow errors. Uh, yeah, it increases super, super fast here. Like, look at that. Those numbers right there. 121. Oh, now that I'm thinking about it, the overflow errors make a ton of sense. Because as you go to infinity, right, this function will go to negative infinity, right? Because the x4 term dominates. So as you go higher and higher, the fact is that your your things will become negative, more negative and negative. So it makes sense that this overflow error is starting to occur. Yeah, that makes sense. Okay, let's switch out the function here. So let's do we have to import math, I think, for this. I don't know how you do this without importing math. You could do a Taylor series maybe. Yeah, but I mean, we'll just keep it simple. So it'll be sine of x divided by, oops, divided by 1 plus x cubed. Okay, just intuitively, just looking at that question, let's think about where we'd find the minimum. Obviously, x equals 0, but not there'd be a ton of minimums. Does this ever become negative? Oh yeah, it does. It does. It does. After pi over 2, after pi, sine of pi becomes negative, so it can be anything in that range, and probably when sine equals -1, 3 pi over 2 plus n pi. The bottom could never become negative, so I think it would be 3 pi over 2 about. Anyway, the derivative of this, we could work that out using quotient rule. So for example, 1 plus x squared, it'd be about, oh, that gets kind of complicated. So you know what, I'm just gonna plug this in. It gets a little bit complicated because even the bottom doesn't get minimized. So yeah, okay. Yeah, I was kind of concerned when I first saw the fact that it was um yeah, I was very, very concerned when I first saw that, like, there was a, when I first saw that there's an overflow error, and I thought that I made a mistake in my code, but it turns out it makes tons of sense. Uh, cancel. I suppose if you wanted to avoid local minimums, the starting point is very important. So I'd start from 0. Seems like a solid starting point, mostly, so that um, or what we could do is we could actually plot this using matplotlib or something, but it doesn't sound very fun, so we will not be doing that. Whatever, whatever. Okay, yeah. So yeah, it's pretty complicated, but let's just type. Okay, yeah, we got the function. We got ChatGPT to helpfully type this out. Thank you to ChatGPT for doing this for us. Thank you again, ChatGPT. Where did I do this? Math app. Let's just make that. I don't know why. I could have just kept it as math for clarity's sake, but first of all, I don't know what's up with me. What? Sorry. What am I doing? Why am I? Why am I not squaring it? Also, where's my parentheses? I mean, please. I could even calculate them separately, just divide them, but I chose to put them all in one thing to just make it kind of negative 0.43. Uh, let's change the number iterations, I think. That's not enough. Let's go. Okay, maybe not that much. My computer might lag actually. Well, it's a single variable radiant descent. It's not particularly complicated, so it should be able to run this pretty easily. No difference really. So negative 0.4371 is that a good min of sine x? Let's verify this with a calculator. Or you know what? I'm just gonna use. It's pretty decent here. Dude, AI. Dude. Also, what am I doing? Why is it? Why have I? Why do I have a set? Okay, I might have forgot that we could have done flow inf. I forgot we could do flow inf. Wait, right here. I forgot that here we could just replace this line of code with flow inf. Just replace this line of code with flow inf. I keep getting this as a min. Okay, so you know what? Let's graph. Let's go to Desmos. Let's graph this behavior. Let's set a line at x equals. Because maybe I've done something wrong with my way I've set the functions or something. I need to lock in a little bit. Because it seems perfectly correct for gradient descent. Also, I need to remove this print. Remove the try except block. That is definitely kind of slowing things down a bit. Not that speed is really a problem right now. Speed hasn't been a problem. So we're doing sine of x over 1 plus x Okay, sine of x. This is a pretty good value. This is a pretty good thing to do with it because it has pretty much one min. It has a min, and it is a. Oh yeah, we're right. Yeah, it is. It is. It's correct. It's correct. We did it correctly. The reason is I actually looked for the x value. Very foolish of me. Yeah, I think we're pretty good off right now. We could do the second one, multivariable gradient descent. Here, we need to actually like vector sense. So if it's like that, we have to work out the gradient first. That should be, if we're looking for df by dx, right? So by can you see that? Can you see this? You can, right? Yeah, I'm pointing here, but can I open like MS Paint or something? Let's open MS Paint. Am I even streaming? I can't even tell. Like if I go to YouTube, do I see my stream? I can't even tell. Let's just check real quick. Not that I have particularly anyone really watching my stream. Should turn on display capture to do this. Yeah, we're live. All right, cool. Let's quickly just talk about what this math means. Um, okay. So what does this mean when you talk about multivariable gradient descent? So let's say you have a function that takes in x and then y. Let's say it's equals to, well, we'll just do the one given in the example in the thing. So it's what? Can you see my screen now? Oh, I have to put my, yeah, okay, you're able to see it. So as you see here, we have x sine y plus x squared. So let me just erase this real quick. X sine y plus 2x squared or something. X sine y plus. Dude, my memory's okay decaying, honestly. So anyway, x sine y plus x squared, right? So by the multivariate chain rule, right? If you're taking the derivative of f with respect to x, sine y is treated as sort of a constant, right? So when we do, I think the future is whenever we do problems like this, we're going to try to derive everything ourselves. So if we take df by dx here, it'll be equal to sine y, because that's treated as a constant, because x and y are independent, plus 2x. So let's just verify that result with what we got here. Sine y plus 2x, yep. And let's now derive df by dy. So df by dy, right? If we're taking the derivative of this, x is treated as a constant. So it's just x multiplied by cosine of y. And the derivative of a constant is just 0, so it's just plus 0. So x times cosine of y. Yep, that's exactly right. Okay, cool. So now we just do the same chain rule, except we update, for example, we create a matrix here. So we have a matrix of our initial x values, x and y value. So we multiply alpha. That's supposed to be alpha. I don't know if you can tell very well. You do df by dx, and then you do df by dy, and that's how you do multivariate gradient descent. So multivariate gradient descent is pretty important, especially when you're dealing with like neural networks and stuff, because by neural networks you have a cost function, and you'll be finding the derivative of the cost function with each weight, and you'll be adjusting the weights. So if you just random kind of segue here, if doing this, you just do derivative of the cost with respect to the dz multiplied by dz with respect to the cost. But let's get into that later, I suppose. Instead, we should just probably try to do this problem now and stop getting off topic. I guess I have a tendency to get kind of off topic there. But if you are learning and doing gradient descent for neural networks, that's how it would sort of work. So we'll do part 5 exercises. I could write tons of tests for this, but I think it's fine to leave this as it is because we can literally verify a couple by hand, and as long as the principle holds, it should be working. Okay, yada yada yada. We sort of understand how to minimize it, so we understand how to minimize the thing, I think, and I think we're pretty good. Ooh, dude, that's pretty beautiful, isn't it? The fact that this is exactly what you're doing, but when you have more sort of when you're doing a neural network and training it, trying to minimize a cost function, that's sort of what it looks like. But the cost is like a lot more complicated and wavy. But you see how it's like this, and you go easily to the correct answer. When you're doing it based on batches of input and outputs, you will be training more like this, but it'll eventually converge. Whatever. Sanity check. Gradient descent. It is difficult to verify. So we have this function. So it's not too different from how you do a normal one, but I'm just gonna go turn the fan on because it's getting kind of hot. So as we sort of established and look at the textbook, you could read the textbook over and try to understand if you're still a little bit. So let's create another gradient descent, but maybe we should name it multivariable. Let's name it multivar. I think var gradient descent. Multivar gradient descent. Um, sorry. I should pass in alpha, obviously. In Python, you have to put in the at the end because the other things you want to put in, so it's just iterations. Well, in this case, let's set it to 10,000. Be sort of getting decent value. We could check the conversion early if we really wanted to. But we could copy everything from the last one, but we'd need the function of the gradient. Function of the derivative. Sorry. What are gradients? Gradients are just the what are gradients? Yeah, gradients are just the matrix of the derivatives evaluated. That's the gradient because it tells you how much you're going to change by. So let's keep. So we're doing a double multi. Um. Okay. So is there a way to check how many? Um. If there is, what we could do is we can make this optimizable based on how many of our functions you wanted. So what we could do is let's just check if we are going to be doing that. Yeah, we are doing 3 functions. Okay. So um. So um. So at the start, I think we say we find the number of arguments. Uh, well, do we have does this involve importing a library called inspect? I hope not. This is what I got from just googling it. Well, sorry, not googling, ChatGPT. Uh, I don't know why my there's like a there's like a problem now. You literally can't see my yeah. There's no way. How could this just okay? That's unusual. I guess it just sort of disappeared. My file just like files running from VS Code just kind of disappeared. Um, yeah. All right. So let's stay on topic here. We're doing multivariate gradient descent. So apparently, check the Python documentation, whatever, and apparently, this is the way to do it. But instead of having a function, let's replace this with a function, right? So we get the number of arguments, which is pretty helpful, and then this tells us how many variables we need to basically um, put, yeah. But um, so one way we could do this is we could okay, so we could basically say uh okay, you know what? We could just do something boring, which is if num args if it equals 2, then x is equal to wait. Okay, yeah, there doesn't seem any easy way to do that. So let's just go to let's just okay, let's just check then. If num args is equal to 2, then yes, so then if it equals 2, then we know that x and y are gonna be our 0, except for 0. Elif, um, yeah, let's just say else. We'll assume there's only gonna be 3. Then x, y, z equals 0. So these are the current z. Um, uh, then also say that variables equals x, y. Okay, so now we need to basically copy a lot of the code from our last one. Literally just copy it, but a couple things we need to change are the first guesses. The way variables work. Because there's going to be, reason these variables are important is because instead of uh, first guesses, we need a first guesses, we need first guesses to be a list of lists. And we need that to contain all the possible values. Yeah, so uh yeah, so okay, so a couple things. Instead of for I in first guesses, we should do for uh okay, you know what? I think there's probably a more efficient way to set these variables, but I'm just gonna do the lazy way approach. Um, maybe this isn't the best way. It probably isn't. Generally, you don't want to do the lazy approach. But I'm just gonna say, or I could just say equals I. I'd already but so variables equals current x guess. So you take the variables. Um, uh, okay, this is gonna be a very ugly way to do this, and I'm sure I'm probably people are gonna be like, "Why would you do it this way?" Sorry, like, wait, you're trying to minimize. Sorry again. Yeah, you're still given a function. Okay, so you're trying to minimize. Okay, so variables. So you have to do the current variables. Uh, so let's do a minus b for a comma b in zip. Now what do we zip? We need to zip up. I'm sorry. What we need to zip is we need to zip. We need to zip the two functions, bro. Right? So what do we need to zip up? Sorry, zip. We need to zip the values that We need to zip variables. Come on, insert, right? Yeah. Comma. We need to get the second one, so we need to do. Uh, so basically, we need to do derivative of variables. List. So we need to make sure it takes the derivative takes as a list. And it's not a minus b, it's just a minus alpha times b. Order of multiplications, those parentheses, so it knows just to make sure for our readability, you know that happens first. And then what do? We append we append the variables. So variables are a list. So we need to append the variables so we can keep track of those variables. So we print potential mins. We don't need to do that. Current track function dot num. This should still work because it should try the thing. So we have the function taking a list as well. Is there any time where we don't take a function doesn't take a list? No, we're good, I think. Uh, so did we even use this? But I don't feel like we didn't even need this. Because we have the first guess anyway, so this doesn't even matter. Oh, but this is assuming, this is assuming there's three, right? Yeah. Uh, 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 okay, going back, we might have needed that. We might have needed that. For I. Yeah, this took a second. So let's just actually write out the functions really quickly. What's the first function? So func1 uh return it takes the input as var as well. So we do is it's pretty simple. So we do x comma y equals vars. We should be able to unpack that way. So that's pretty cool. Vars. Yeah. So it's pretty cool. So let's just check. if it works. Oh, sorry, we have to actually call it. So let's do print multivariate percent. Oh, yeah, percent. And then what's the function? One derivative. We're just calling it the derivative, right? Uh, iteration. I think we're good there. Let's just print it. Uh, Run it in dedicated terminal. Oh, we have to take the derivative with respect to f and derivative with respect to x. Oh, we completely forgot to do that. Okay, that's kind of funny. Kind of embarrassing, but let's just that didn't happen. Let's just say that. So okay, so we need df. Let's say d so x. Say the derivative with respect to x. That's gonna be so 2 multiplied by x minus 1. That's it. That's it. Yep. And dy, d sub y is going to be equal to that's going to be a constant. Obviously, it's going to zero out. So the derivative of a constant is obviously 0. So that's going to be 3y squared, and then 6y. So it'll become 6 multiplied by y. So then we just return d sub x comma d sub y. Whoa, see if that works. We're running dedicated terminal. 0. Kind of surprising. Which I'm gonna ask ChatGPT what's the minimum val of this function. I think it would be 0 maybe. These are all gonna be obviously positive, so the only way it's minimum is gonna be at 0. Critical points. 0. Okay, yep, it works. Should we even okay, fine. We'll write one more. We know how to do this, we can just add another variable pretty easily. Or does our function already allow for multivariates? I think it does. So let's just test that out. That would be a pretty fun way to find out. So why not just make this y minus 2? So I think we should already test for multivariables. So y minus 2 is there. Plus 4 multiplied by z plus 1 squared. Yes. And that should be one of theirs. X, Y, Z. So we're assuming there's 3 variables now. So x, y, z is what's returned. And oh wait, whoa. There's a quick problem. Arg count. Because we're passing in num and potential mins. So we're taking in bears as a list, right? So bears is not actually counting the correct number. So let's just pass in num args here. So and let's just set num args equal to num args. 2. And then we can just go in here and instead of doing this whole thing here, we can literally just say num args equals num args. And instead of that, we can literally just eliminate this num args variable altogether. And we can have a potentially more concise function. We just need to make sure to specify that num args is not going to equal 3. Not going to equal 3, which is pretty cool. Yeah. So boom, bam, bop, bada bop, bop. Okay. So yeah. So we need now d sub z, and we also need to add z here. This is pretty fun. I'd say this is pretty exciting because we're actually applying some pretty fun concepts here. So that also just this is a pretty easy function because these were just 0 out. These are all just 0 out except for that. So that would become 8 z plus 1. 8 multiplied by z plus 1, and you can obviously see why the multivariable chain rule holds here. Multivariable chain rule seems it's pretty intuitive to grasp here. So you just need to know the basics to be able to do this. Let's see if this works. All right. Oh, we just made a simple error here. It's I don't know how. I keep forgetting. This stream, I'm just all over the place. 12. That's an interesting value. Let's now test out. Let's ask GPT what the minimum test would be. We are testing it over a decent amount of variation. That is true. That is true. Um, the val of this function. Okay, cool. Let's check it out. ChatGPT, does it concur with our calculations? I do not think it agrees. I do not believe it actually agrees. I mean, our things is 12. Disappointing, rather. It's not too disappointing considering it's part of what happens here. So a couple of things. So first of all, this grade is correct. Is calculated incorrectly. It should be 1 minus 2, right? So maybe that's part of why it could be happening. That would affect a decent bit, right? This gradient is being corrected correctly. Whoa, kids speaking English. All right, let's just test this out now. 1.12 and whoa, this is like 0.001. Yeah, this is a really, really small number, almost approaching 0. So what we're gonna go ahead and do here is we're gonna change the number. We're just gonna change it in here because we're like, why it doesn't matter too much. But the problem is the the reason this might not exactly get to 0 is pretty interesting. So let's just check. This will take a second. Yeah, about the same. The problem is when numbers get really small, right? These z's are gonna get really, really small. The gradients should still be decently large. Uh, the gradients should be decently large, but the gradient of x is going to be like -2. This is going to be about -6 all the time, and about 8, so it might cause some just jumping around. But maybe what you could do is you could make the gradient actually decay, but it's fine. I think if we get a good enough value, let's do it one more time. Just to prove to ourselves that we've done a decent multivariate gradient descent. Okay, sorting algorithms. I'm very bad with sorting algorithms, so this should be my bane, I suppose, I'd like to say. Not too good at sorting algorithms. I just don't do it much. I suppose I just don't do them enough because like this sort of gradient descent, I'm very very familiar with, but sorting algorithms, not too much. Okay, many different methods of sorting items in arrays. So let's go over some of the simplest methods. I've heard bubble sort is pretty good. Merge sort, I don't know what merge sort is, but obviously people use merge sort. The absolute simplest sorting method is selection sort. Minimum. Oh, but from the original. Yes, we just append it. Bubble sort is pretty cool. Bubble sort is pretty cool. Feels pretty intuitive. I could definitely code that pretty easily. I feel reasonably confident. We could code this. So let's do My computer's low key getting a little bit hot. GPU usage. Bubble sort pretty simple. Insertion sort. Um. Oh yeah, where were we? Sorry, we were supposed to do counting sort. Counting sort. Dude, sort algorithms is a little bit confusing. Especially the time complexity. When they ask you the time complexity of a sorting algorithm, I'm like, don't know. Like, but time complexity, they're like, oh, actually, it's O of n. I'm like, I don't know how it would. I mean, normally I get it that if you're like, okay, if you're iterating over for loop twice, that's n O of n squared, I believe. But I don't know when it's O of n. This is actually like okay, counting sort seems so confusing, but very exciting to learn. More about sort algorithm. Whoa, 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 whoa. That works. That does work. It's kind of fascinating. Count sort is what is count sort? Yeah, O of n squared. That makes sense. If Okay, we need to actually read this part. Okay, selection sort. Lots of memory. Makes sense, especially if you're working in non-memory memory safe things. Calc min. Um, bubble sort. Yeah, this is like really important. But unfortunately, I think I have to do other stuff. Unfortunately, but let's just see. Let's just read over. Merge sort will be next. Objects. Okay, we'll be doing matrix. We'll be starting with matrix multiplication. Let's just go back to sort of look over how far we've gone through before I end this stream. Whatever. Yeah. Okay. So we've done. We're doing about to uh sorting algorithm. And finally, here is where we implement our first k-means clustering. It's going to be very, very useful in the future for me, especially. Hash tables, very important. Uh, like hash tables for transportation. I can't talk today, apparently. Regression is pretty useful. Overfitting, underfitting. This is very useful. Regression, k-means, like native Bayes, graphs. That's pretty useful. By the end of this, I'm going to be kind of cracked, to be honest. Because there's stuff in here I do know, like Minimax, right? I can implement the Minimax algorithm for most games. But there are stuff in here that I have just absolutely no idea. Like, let me scratch, I can do this. But something like K-nearest neighbors, honestly, that's a basic machine learning algorithm. I do not know that. Maybe I should, but yeah, and obviously I really want to do 124. That would be such a fun thing to implement. But for back propagation is so fun. I know that, but there's something here I do not know. And I would want like, come on, bro. I do not know. This sounds fun though. This sounds really, really fun. But before we get to that, I think that it's about time I end today's stream. Oh, can you not see my technical? Oh, yeah, okay. It's about time I end today's stream. Uh, yeah, it's been pretty fun. I think we're gonna finish part six rapidly. We're moving through it very, very rapidly. You see, we're on part six almost. In how many parts is it? Part 11. So we only have like maybe two more parts. Let's see, we're on 12. So we have one more part, and we kind of sped through this. We are really moving. So yeah, I think we're gonna end it here for today because I have a little bit of other stuff I need to work on. Thank you guys for watching. I don't think there's particularly anybody really watching, to be honest.